Binary search looks like it needs a linear scan, but there's a halving trick that drops the work to logarithmic time. We're given a sorted integer array and a target value. The task is to return the index of the target if it exists, otherwise return -1. For example, with the array -1, 0, 3, 5, 9, 12 and a target of 9, the answer is index 4 because 9 sits at that position. The naive way is to walk through the array from the start, checking each element until we either find the target or run out of items. That linear scan runs in big O of n time and uses only constant extra space, but it ignores the fact that the data is already sorted, so we waste a lot of comparisons on large inputs. Because the array is sorted, we can discard half of the remaining candidates each step. We keep 2 pointers, left at the start and right at the end. While left is less than or equal to right, we compute a middle index as left plus the distance to right divided by 2, which avoids overflow. If the middle element equals the target, we're done. If it's smaller, we move left to just past the middle. If it's larger, we move right to just before the middle. When the pointers cross, the target isn't present, and we return -1. Let's trace the example. Start with left 0, right 5. Middle is 2, value 3, less than 9, so left becomes 3. Now left 3, right 5, middle 4, value 9. We found the target at index 4 and return it. You'll recognize this pattern whenever you see a sorted collection and need to locate a value or a boundary. Any problem that lets you throw away half the search space each iteration. The algorithm runs in big O of log n, logarithmic time, because the search interval halves each loop, and it uses big O of 1, constant time extra space, since we only keep a few integer pointers. Try the next problem, same pattern. If you found this helpful, hit subscribe for more pattern-focused DSA walkthroughs.